Okay, so when we last left off, we had talked about the rules for drawing, for comparing possible structures. So we said structures that follow the octet rule are generally more stable. Structures with lower formal charges are generally more stable. Structures with formal charges prefer to have positive on the less electronegative and negative on the more electronegative. So let's use these rules and decide which one of these two structures below is preferable. So talk about it at your tables for a few seconds. Look at your rules. Decide which one of these two structures is preferable. All right. So I pulled a card. Caitlin, which one do you think is more stable? And why do you think this? All right. So the answer was the one on the left because, let's look where the formal charges are. Negative formal charge. And then negative formal charge. This one is more stable because oxygen has a greater electronegativity than carbon. So oxygen is happier holding on to that extra electron than carbon would be. I shouldn't say happier. It is, due to its stronger electronegativity, is more capable of holding on to that electron than carbon would be. But as you can see, all the octets are filled. It's just this one is more stable. Yes. The question is, should we memorize the electronegativities because they're not given on the periodic tables? There are the ones you should know. Later on in chapter 5, I think we talk about them. I hate memorization. But you should have some idea. Yeah, it's on page 9 of the notes here. You should generally know. Like you have to know oxygen has a higher electronegativity than carbon. Things like that. Not that this is 3.5 and this is 2.5, right? So just generally, but not what the exact numbers are. Okay. So use the rules to compare the structures below. I didn't put in the formal charges, so you should add them in yourself. Add the formal charges in and determine which is the most stable structure. Okay. As I'm walking around, some people have some done, some people are all the way done. I loved going around and seeing the capitalism. Now, there's fruit snacks being sold. That's why I call it capitalism. So, all right, guys, listen up, please. I saw people doing it really, really well. Like using the formula of formal charge for, say, oxygen. So it has 6 valence electrons. Here it has 4 electrons in lone pairs, 2 bonds, 0. Good. Now, at some point, you're going to be able to stop doing this. You're going to be able to look. Oxygen generally forms how many bonds? 2. So oxygen's good. Nitrogen generally forms how many bonds? 3 from the honk 1, 2, 3, 4 rule. And F generally forms 1. So this molecule, no formal charges. Now, here, oxygen only formed 1 bond and still has a whole octet. So normally, it should form 2, which means this is negative. N normally forms 3, it's checked. Fluorine now, fluorine generally, not only generally, fluorine always just forms 1 bond. So this one is plus, and this is like super duper not good. You never put a positive formal charge on fluorine. Fluorine is the most electronegative element. You're never going to put a positive formal charge on it. All right. So we move over here. Fluorine, 1 bond, good. Oh, oxygen, 3 bonds instead of 2. Nitrogen, 2 bonds instead of 3. So this is not good. So our winner is the one over here with the least formal charges. All right. So you can evaluate different structures to determine their stability and the best, I put in air quotes, best way to draw it. And your problem set 5 is going to be a lot of this, a lot of practice. I think this is one of those things that the more you practice, well, it's true of anything, but like you begin to see it after you practice for a little while. Like I did here, you can go through and count the formal charges using the formula, but once you get some practice in, you just look at it and you can understand the formal charges and the stability. Okay. Comparing structures. An atom that's very electronegative, like oxygen, does not bond with itself if it can avoid it. So if oxygen can bond with something else, it usually chooses to bond with that other thing. So the formal charges, this one has no formal charge. And this one does. The bottom one is actually more stable just because oxygen isn't bonding with itself. Yeah. So the question was, would you get molecules that are as linear as the one on the top? No. For whatever reason, the one on the bottom is shown in the 3D orientation, and this is not. So this is not actually linear. Which is an interesting segue into, for those of you at home who are watching, that is a tremendous segue into what you're going to be watching next, which is all about molecular shapes. So Ben did a great job seeing into the future and knowing what we're going to talk about next. Right. So Ben was just showing me an example of something you could have that would be linear. That's a longer chain, but generally, so don't put oxygens together. Boom. The only time we generally see oxygens bonded together is oxygen gas, which is fine because it's just itself, and hydrogen peroxide. Hydrogen peroxide has 2 oxygens bonded together, but it's pretty reactive, so the oxygens don't like to be bonded to themselves. They'd rather be bonded to something else, something weaker. And fluorine would fit in here too, but fluorine can never be the central atom because fluorine can only bond once, so it can never be in the middle here and bond with itself and something else, right? Okay, so summary. Make sure you have the right number of electrons. Follow the octet rule if you can. Try to minimize formal charges if you can. Lots of techniques exist. If you go into, I think the next page on your notes packet is ways to draw Lewis structures. So use that as a guideline. If you're getting stuck, use that guideline to help you draw Lewis structures. There are multiple ways to do it. Find what works best for you. And practice some more until you find your proper technique.